So this is the division algorithm. For natural numbers. So the theorem says if we have two natural numbers, n and m, so natural numbers, and n is less than or equal to m, then either there is a q in n so that m is equal to n times q, or there are q and r in n so that m is equal to n times q plus r, where r is less than n. Okay, so roughly speaking, this theorem tells us if you have two natural numbers, one is less than or equal to the other, then you can always use the larger one to divide the smaller one to divide the larger one, and either the smaller one divides the larger one, that is the first case, m equals to n times q, or if the smaller one doesn't divide the larger one, then there is a unique remainder r, which is less than n. Okay, so this is the meaning of the algorithm. Okay, so let's see how we use the properties we just reviewed to prove this division algorithm. Okay, so let's look at the proof. We'll first construct a set and show that the set has at least one number. And we use the property to say that set has a smaller. What did you say? Okay. And we then use the property to show the set has a least member, the minimum, and we'll construct the Q as we required. Okay. So, well, so assume we have two numbers, n and m are natural numbers, and n less than or equal to m. This is our assumption. Okay, then we'll define the set S to be the set of all natural numbers k so that n times k is greater than or equal to m. Okay, so so this is the k, So I look at all such case, natural numbers k, so that n times k is greater than or equal to m. Okay, so for example, if n is equal to 2, m is equal to 3, then this k starts from 2, and 2, 3, 4, and keep going. So all those k's are in the set S. Okay. Now, but we have to prove, first prove S has at least one member. We first prove that S has at least one element. So actually we can claim that the number m is belongs to S. Okay, m belongs to S. In other words, what we want to show is n times m is greater than or equal to m. So that is equivalent to n times m is greater than or equal to m. Okay, so because this, if we prove n times m is greater than or equal to m, by the definition of the set S, m belongs to S. But this is more or less obvious since n is a natural number. So we know n is greater than or equal to 1. So because 1 is the smallest natural number, the starting number, then we use the algebraic property. If n is greater than or equal to 1, we multiply the same number with same natural number, we keep this equality. So n times m is greater than or equal to 1 times m. So this is the algebraic property. You multiply the same number, same natural number, you keep the inequality. This is exactly n times m is greater than or equal to m, because 1 times m is equal to m. All right, so we proved the first claim. M belongs to S, so S has at least one member, M. So since S has at least one member, by the property of natural numbers, S has a minimum. So we denote the minimum to be Q. Okay, let's change the notation. Let's use P to denote the minimum because the theorem uses the letter Q. So let's use P to denote the minimum. Okay, so at this stage, we get a candidate here, P, which is the minimum of the set S. Okay, now let's look at the properties for this minimum P. So since P is the minimum of S, P satisfies two properties. So the first one is, since P is in S, we have N times P is greater than or equal to M, because P is a member of S. So by the definition of S, N times P is greater than or equal to M. Now the second property is, if we have any natural number less than P, if X is less than P, then X is not in S. So the second property uses the minimality of P, because P is the minimum. So you can't get another smaller number containing S. So that is N times X is less than M. Because X is not a member of S, which means X does not satisfy the condition of S. So N times X has to be less than M. All right, do you have any questions so far? So
what's the difference between P and Q?
Oh, what's the difference between P and Q? Next, I'm going to show you the relation between P and Q, okay? I'm going to construct a Q from P. P is just a minimum of S, and then we want to construct Q using this P, all right? Okay, so so in this situation, we have the minimum of S and the two properties for this minimum. Now there will be two cases. So there are two cases. The first case is, since we know N times P is greater than or equal to M, it is possible that N times P is equal to M. This is the first case. The inequality holds for number one, for property one. So in this case, we just let Q be equal to P. Then N times Q is equal to M. Okay, so if the equality holds for property one, Then we have, we just let Q be P. We have N times Q is equal to M. Okay, so this is a simple case, but the second case requires a little bit work. So the second case is N times P is strictly greater than M. So the equality for property 1 doesn't hold, strictly greater than M. Then by the property of natural numbers, then there exists one thing we have to argue before we make this claim. And since MP is greater than M, then we can claim P has to be greater than 1. So anyone understand why this is true? Why? If MP is greater than M, P has to be greater than 1. Right, great, because our hypothesis says N is less than or equal to M. So if you have N multiply a number is greater than M, then this number has to be greater than 1. Because if it's less than, if it's equal to 1, then this contradicts with this condition. So P has to be greater than 1. Good. Okay, since P is greater than 1, recall the properties we had. Any number which is not the initial number of the natural numbers has an immediate predecessor. So in other words, there is a Q in N so that Q plus 1 is equal to P. Because Q is actually the immediate predecessor for P. Okay, this uses P is greater than 1. Okay, now we know since Q is less than P in this case, so we know that Q is not in S because P is the minimum of S. Any number which is less than P is not in S. So this is the second property here. Okay, any number that is less than P is not in S. And we have also N times Q is less than M. This just uses the second property. All right, so we actually get three conditions. So the first one is N times P is greater than M. And also we have Q plus 1 is equal to P. And then we have N times Q is less than M. So let's move this three property to next page for our convenience. So we have the three properties. So from last page, we actually have the three things is N times P is greater than M. q plus 1 is equal to p, and n times q is less than m. Okay, we have the three properties. Okay, now since n times q is less than m, so we know that there is a r in n, so that n times q plus r is equal to m. So what properties of the natural numbers justifies this? That is, every natural number which is larger than the other is a eventual successor of the smaller one. So you always find a natural number r, so that the smaller one, n times q plus r, is equal to m, the larger one. All right. So now you see the form is essentially there. M is equal to n times q plus r. So we have one last thing to justify. That is the r, the remainder, is less than n. We want to show this. Okay. So now we are going to use these two properties to justify r is less than n. So we know that nq plus r is equal to m, but m is less than by the first inequality there is n times p. Okay, but p is equal to q plus 1, so this is n times q plus 1. So if you look at the left end, which is nq plus r, the right hand is n times q plus 1. So what you actually get is the n times q plus r is less than n times q plus 1. Now you just multiply out the numbers, use the distributive property for natural numbers. Hence, n times q plus r is less than n times q plus n times 1. So you see the n times q get canceled out. So therefore, we get r is less than n times 1, which is n. Okay, so at this point, we finish the proof. Okay, so let's just go over strategy for the proof. So we want to prove for if we have two natural numbers, n and m, n is less than or equal to m, then you can always write m as n times q plus or n times q plus r with r less than m. So we actually construct the set S and prove S has a minimum. And then we use that minimum P to construct our Q. Essentially, the procedure uses the basic properties for natural numbers. Okay. All right. So this is a division algorithm. So you can always divide a natural number to get a remainder. Okay. So any questions about this proof? This is the first abstract proof you've ever seen. So if you have any confusion, please ask. Okay, so next let's review another theorem we used last time. That is the mathematical induction. Okay. Let's recall the statement of the theorem. Of induction. So we'll let Pm be a statement that is either true or false. For each n in n. So if the following statements are true, if n is equal to 1, then Pn is true. And the second is if for n equals to n0, Pn is true, then for n equals to n0 plus 1, Pn is true. Then for all n in n, Pn is true. Okay, the theorem of induction says if you want to prove some statement Pn about natural numbers is true, then you have to prove the following two things. The first thing is you check the initial case, which is for n equals to 1, the statement P1 is true. Okay, that's the initial step. Now, the second step is you assume, okay, so this is the additional condition you can use for mathematical induction. So if you assume for n equals to some n0, the statement is true, then you have to justify the next, for the next element n equals to n0 plus 1, the statement is also true. This I explained, roughly speaking, is like you are putting a series of bricks on the ground, and if you, the first step is to push down the first brick. That is to verify the initial statement is true. And then if you assume one of the bricks in the series fall down, then the next brick falls down. That is the second one. Okay, if n equals to n0, Pn is true, then the next one, n equals to n0 plus 1, Pn is true. So once you verify these two things, you can claim the statement Pn is true for all natural numbers. Okay, so next we are going to prove the theorem of induction using the properties of natural numbers.
I have a quick question.
Yeah.
It says it's recording. Are you going to upload these onto eCourseWare?
Okay, so as I mentioned in the first class, so since the university wants students to participate in Leaf's lectures. So in general, I'm not going to put this video online because otherwise students would just quit attending classes, only just watch the video. But in case you have some emergencies or some special reasons, you can send a request. I can let you to watch the recorded video. But in general, we don't send out the link, okay?
Okay. I just have work scheduled. They scheduled me wrong, so I'm gonna have to leave a little early.
So if you can provide me a document from your employer, and
Okay.
then I can you can send me a request, so I can send you the link, okay?
Okay, thanks.
All right, so let's just try to prove this theorem of induction using properties of natural numbers. Okay, so let's look at the proof. Okay, so we'll define the first set A to be all the natural numbers so that the statement Pn is false. So let A be the set of all natural numbers so that Pk is false. Okay, so for this set A, there will be two cases. So the first case is A is empty. In other words, A has no member. No member is in A. So if A is empty, what does it mean? No natural number satisfies Pk is false. So in other words, for all natural numbers, Pk is true, right? That is no K in K, K in N, so that satisfies Pk is false. No natural number satisfies Pk is false, which means all natural numbers satisfy Pn is true. Okay. So for all n in n, Pn is true. So this case is a simpler case because there's nothing to prove. It's already true. So case 2 for the set is A has at least one element. Okay, A has at least one element, and moreover, A is a subset of the natural numbers. So A has a minimum. Any non-empty subset of the natural numbers has the minimum. Okay, let P be the minimum. Okay, since P is the minimum of A, then we know P okay, so I have to justify one more thing to make this claim. Then P is not equal to 1. So why P is not equal to 1? Because you look at this theorem. The first case when n equals to 1, the statement Pn is already true. So the initial case is true. But our P is a member of A. A is a set of natural numbers which fails the statement P. So that's why P is not equal to 1. Since P is not equal to 1, we can say P is greater than 1 because 1 is the initial element of the natural numbers and greater than 1. Okay, since P is not the first element of the natural numbers, then we can claim P minus 1 is also a natural number. So P minus 1 is its immediate predecessor. Okay, you have the immediate predecessor. Moreover, since P minus 1 is less than P, we know that P minus 1 is not in A. Because P is the minimum of A. So any number which is smaller than P cannot be containing A. So P minus 1 is not in A. So P minus 1 is not in A, then we have to interpret this. So any member which is in A satisfies Pn is false. So any member which is not in A satisfies Pn is true. Hence, the statement P of P minus 1 is true because P minus 1 is not in A. However, if you look at the second property, second condition for the mathematical induction, if Pn is true for some n0, then Pn is true for n0 plus 1. So for the next one, Pn is also true. Okay, so if Pn minus 1 is true by property 2, P of P minus 1 plus 1, so next one is true. So that is P of P is true. If the statement for P is true, then this P cannot be in A. We get a contradiction. Because P is the minimum of A. In particular, P, little p is containing A. But from this assumption, we get P is not in A. We get a contradiction. So actually, what this proves is that the set A has to be an empty set, because if A has a list element, we reach an obvious contradiction. Okay, obvious contradiction. So you can see the proof is pretty much uses just using the properties of natural numbers and the conditions for the induction of the theorem of the theorem of the induction. Okay. Okay, so let's again summarize three basic types of proofs. The first one is a direct proof. Okay, you start from the hypothesis and assumptions to reach your conclusion. The second one is mathematical induction. And the third one is by contradiction. So you can see just now in the proof, we've already used the third one, by contradiction. Okay, because in the second case, when we assume A has at least one element, we just use basic logic and to reach an obvious contradiction. So this would tell us when you reach the contradiction, this tells us your hypothesis A has at least one element cannot be true. That is, the first case has to be true. A has to be empty. So essentially, just tells us this. Okay, so let's try to use mathematical induction to prove more examples. Prove that one plus 3 plus 5 plus up to 2m minus 1 is equal to n squared. Okay, so we'll use mathematical induction to prove it. So if you recall the mathematical induction, the first step is to verify the initial case. So for n equals to 1. So the left side is equal to, okay, when n equals to 1, the left side has only one term. It's just one. So it's just 1. And the right side is equal to 1 squared. Is also equal to 1. So we have left side equals to right side. Okay, so the step 1 initial case is simple. You just compute the left side and compute the right side by plugging 1. Then you get equalities. Okay, the important thing is the second step. So this is what we want to prove. Let me write it again. 1 plus 3 plus 5 plus 2n minus 1 is equal to n squared. Okay, step 2 is, okay, so we assume for n equals to n0, the statement is true. So that is 1 plus 3 plus 5 plus up to, when n equals to n0, that is 2n0 minus 1 is equal to n0 squared. Assume Pn is true for n equals to n0. Now we want to prove for n equals to n0 plus 1. So we want to prove this case is also true. So in this case, what left side is equal to, you have to write it down correctly. So it's 1 plus 3 plus 5. So what is the last term? Is 2 times n0 plus 1 minus 1. Because n equals to n0 plus 1. Okay, but you have to realize this summation is actually by adding one more term to the left side of the previous equality. So this is equal to 1 plus 3 plus 5. So the term before the last term is actually 2 times n0 minus 1 and 2 times n0 plus 1 minus 1. Okay, I just write down the term right before 2 times n0 plus 1 minus 1. Okay, so at this stage, we are going to use our assumption here. You see, 1 plus 3 plus 5 plus up to 2n0 minus 1. But by our hypothesis, this is equal to this n0 squared. So this is equal to n0 squared plus 2 times n0 plus 1 minus 1. So this is by assumption. Let me denote this one by, say, star. Okay, by assumption star. Okay, so we can continue our computation. This is, let's multiply out this 2n0 plus 2 minus 1, which is n0 squared plus 2n0 plus 1. So this is exactly n0 plus 1 parenthesis squared. Okay, so you can see in step 2, what we did is we assume for n equals to n0, the equality holds. Now, for n equals to n0 plus 1, we first compute the left-hand side. And when we compute the left-hand side, part of the summation appears in the hypothesis star, assumption star. So we use the assumption to replace that partial summation by n0 squared. And then we just use algebraic computations to reach n0 plus 1 squared. This is exactly the right side. Okay, for n equals to n0 plus 1, this is just n0 plus 1 squared is just n squared. So we're done by mathematical induction. So the key for using mathematical induction is to apply the assumption when for n equals to n0 to compute quantities for n equals to n0 plus 1. And what's remaining is the basic algebraic computations. Okay, so any questions about this proof? Okay, so let's look at one more example. Prove that 2 plus 4 plus 6 plus 2n is equal to n times n plus 1. So again, for such a statement, this is about the statement of natural numbers. The most commonly used method is the mathematical induction. So let's prove it. Okay, so for step 1 is for n equals to 1. So you have the left side is equal to n equals to 1. You have only 2 terms. The last term is 2 times 1 is 2, so it's 2. And the right side equals to 1 times 2, which is equal to 2. So we have
how you got the left side, like how you got 2 for the left side again.
Okay, so look at the summation here. So when n equals to 1, look at the last term. Last term is 2 times n, right? So n equals to 1, so the last term is 2 times 1, which is 2, right?
Okay, I got it.
Yeah, so you normally when you look at the summation, when you plug in n, you look at the last term, then you get how many terms appear in the summation.
Okay.
So the left side is equal to the right side. Okay, step 2. Assume for n equals to n0, the inequality holds. So that is 2 plus 4 plus 6 plus 2 times n0 is equal to n0 times n0 plus 1. All right, for n equals to n0 plus 1, so we first compute the left side. So the left side is 2 plus 4 plus 6, and the last term is 2 times n0 plus 1 plus, okay, let me, 2 times n0 plus 1. So again, you need to realize in this summation, the first n0 terms is actually the assumption. So the term before 2 times n0 plus 1 is 2 times n0, and then it's 2 times n0 plus 1. So this is the part you need to use the assumption, okay? So use this assumption. So this is a star. So this is equal to, you use star, the first n0 terms add up to n0 times n0 plus 1 plus 2 times n0 plus 1. So this is by star, okay? Okay, now what you can do is you can take out the common factor. The two terms has common factor n0 plus 1. So if you take the common factor n0 plus 1, you get n0 plus 2. So this is, if you rewrite it, this is n0 plus 1 times n0 plus 1 plus 1. So this is exactly the right-hand side of this equality, because n equals to n0 plus 1. This is n. So n0 plus 1 is n. So, and the second part is n0 plus 1, so it's n plus 1, because n equals to n0 plus 1, this corresponds to n. This is n plus 1, okay? So this is exactly the right side. Right side. Okay, so we actually finished the proof by mathematical induction. All right, so the key step is to use the assumption for the case n0 to deduce the case n0 plus 1. So any questions? All right, so next we just look at a few examples of using direct proofs. Okay, so let's recall last time we talked about the definition of even numbers and the odd numbers. So even numbers, that is n equals to 2 times k. And odd numbers, n equals to 2 times k minus 1. Okay, so these are the definitions of odd numbers and even numbers. So the first result is if n is a natural number, then n is either even or odd, but never both. Okay, so this theorem tells us once we have a natural number, it's either even or odd, but you cannot have a natural number which is both even and odd. So we actually want to prove two things. The first thing is we take a natural number, we show it's either even or odd, and second, show it can never happen at the same time. So proof. So there are two cases for n. The first case is n is equal to 1, the initial number. So if n is equal to 1, well, let just k equals to 1, we get n is equal to 2k minus 1. Then n is equal to 2k minus 1. Okay, this is obvious. N equals to 1, so 1 is equal to 2 times 1 minus 1. So n is odd. So this is a simple case. And assume the second case is n is greater than 1. So if n is greater than 1, then n has to be greater than or equal to 2, since n is a natural number. Okay, when n is greater than or equal to 2, recall we proved the division algorithm for natural numbers. So you have two natural numbers now. One is 2, the other one is n. Since 2 is less than or equal to n in this case, by the division algorithm, so we get n is equal to, the larger one is equal to 2 times q plus r, with r is less than 2. Not r less than, r less than 2. Because in this case, 2 is a smaller number. So the remainder r is less than the smaller number 2. Okay, but you should recall r is also a natural number. A natural number that is strictly less than 2 has to be equal to 1. So let me copy down the condition. So we get this n is equal to 2 times q plus r with r less than 2. Now, since r is less than 2 and r is a natural numbers, so r has to be equal to 1. There's only one case. So that is, oh, I said it wrong. I said it wrong just now. Let's go back here. The division algorithm tells us there are actually 2 cases. Okay, let me erase this. So there are actually 2 cases when okay, since 2 is less than n, then we have either n is equal to 2q or n is equal to 2q plus r with r less than 2. Okay, the division algorithm tells us there are 2 cases. Either n equals to 2 times q or n equals to 2 times q plus r. So if n equals to 2q, then n is even. If n is equal to 2q plus r with r less than 2, then since r is a natural number, then r has to be equal to 1, and n is equal to 2q plus 1, hence n is odd. Okay, to be rigorous, you should realize the second case, n is equal to 2 times q plus 1. It looks a little bit different from our definition, because our definition writes the odd number as 2 times k minus 1. But this one can be written as n equals to 2 times q plus 1 minus 1. So this is still satisfies our definition of odd numbers. Okay, so if n is strictly greater than 1, by the division algorithm, we have 2 cases. Either n is equal to 2q or n equals to 2q plus 1. So n is either even or odd. So this proves the first part of the theorem. The first part of the theorem says any natural number is either even or odd. But we have the second part. N cannot be both even and odd. Okay. Next, we prove n cannot be both even and odd. Okay, so we will prove this using the third method. That's the proof by contradiction. We assume n is both even and odd. Then what by definition n is equal to 2 times k, because n is even, and n is equal to 2 times k prime minus 1, because n is also odd. Okay, so we have 2k is equal to 2k prime minus 1, because both 2k and 2k prime minus 1 equals to n. Okay, let me copy down here. We get 2k equals to 2k prime minus 1. Okay, since 2k equals to 2k prime minus 1, so we have 2k prime is greater than 2k. And by the algebraic property for natural numbers, then we claim k prime is greater than k. All right, so if k prime is greater than k, there is a natural number s, so that k prime is equal to k plus s. Okay. Okay, now let's compute what is 2k prime. 2k prime is equal to 2 times k plus s, which is equal to by the distributed property for natural numbers, which is 2k plus 2s. Now, since s is a natural number, since s is a natural number, s is greater than or equal to 1. So we have 2 times s is greater than or equal to 2, strictly greater than 1. So if you look at 2k prime minus 1, this is equal to, because 2k prime is equal to 2k plus 2s minus 1. This is equal to 2k plus 2s minus 1. But 2s is greater than 1, so this is greater than 2k plus 1 minus 1, because 2s is greater than 1. So this is equal to 2k. Okay, so what you actually get is In this situation, you compute 2k prime minus 1. 2k prime minus 1 is equal to 2k plus 2s minus 1. But 2s is greater than 1, so 2k plus 2s minus 1 is greater than 2k plus 1 minus 1, which is equal to 2k. So that is 2k prime minus 1 is greater than 2k. But if you look at here, in the beginning, on the top, you get 2k is equal to 2k prime minus 1. The contradiction contradicts with 2k is equal to 2k prime minus 1. Okay, so in other words, if you assume the natural number n is both even and odd, so you use the basic properties of natural numbers, you get an obvious contradiction. This tells us this assumption cannot happen. That is, n cannot be both even and odd. Okay, so let's just look at one last example, and we'll be done today. And I'll send out the homework today later. Okay, you can check back either late tonight or tomorrow for homework. Okay, so one last example. If n and m are odd numbers, then m plus m is even. So you want to prove this. So to prove this, you have to use definition. Okay, if you want to prove something is odd, you have to show the number can be written as 2k minus 1. If you want to show a number is even, you want to show the number can be written as 2 times k. So we use the definition. Since n and m are odd, so by definition, n and m are odd. N is equal to 2k minus 1, and m is equal to 2s minus 1. So m plus m would be 2k minus 1 plus 2s minus 1. So this is equal to 2k minus 1 plus 2s minus 1. So it's equal to 2k plus 2s minus 2. So this is equal to 2 times k plus s minus 1. Okay, let me ask you a question. So now I write m plus m as 2 times something. Can we claim m plus m is a even number? Can I? Can we say now n plus m is an even number?
Yes.
Yes. So what about other students? Are you
No.
why no?
Because if you have to act so soon, most likely it's not the answer yet.
Okay, so you're only using this logic, but do you have any mathematical reason?
There's no proof, like they have no values, so you have no proof that like one could be even, one could be odd, so you don't know if it adds up to an odd or even number.
Okay, so let's recall. So if we want to show some number is a odd number, we want to show it can be written as 2 times k minus 1. If you want to show some number is even, you want to show the number can be written as 2 times k. But in this situation, I've already written m plus m as 2 times something, right?
Oh.
This is equal to 2 times something. So it looks like...
Okay, yeah, so yeah. All right, it's even.
Is it even? Everyone agree?
Shouldn't we prove that k plus s minus 1 is superior to 1?
Okay, very good, very good. Actually, you should notice in the definition when we say a number is odd or even, we write it as, so here. Let me go back to the, oh, why it stuck. Let's go back to the definition here. Even number of numbers. You should recall we have a implicit condition here. This k has to be a natural number, right? So this is important. When you say it's an even number n equals 2k, this k has to be a natural number. So you can't just say, for example, k, if I write, say, n equals to 2 times 0, can you say it's an even natural number? Because we are talking about natural number. But 0 is not a natural number, right? So this is not even, or n equals to 2 times 1/2. This is equal to 1. So you can't just say when you write it as 2 times something, but this something has to be a natural number. All right? Understand this definition? So in here, although you write m plus m is equal to 2 times this something, but you still have to verify this k plus s minus 1 is a natural number. In this case, k plus s are natural numbers, so you know the k plus s minus 1 must be an integer. So to show it's a natural number, you have to show it's greater than or equal to 1. So that's what you need to verify. All right, so here you should know, since k is in n and s is in n, so we know that k plus s, not k plus s, I mean k is greater than or equal to 1, because those are natural numbers, and s is greater than or equal to 1. So k plus s minus 1 would be greater than or equal to 1 plus 1 minus 1, which is equal to 1. All right? So at this stage, you can claim.
What?
Yeah.
I'm in the bathroom and on a Zoom call. What's up?
What did you say? Say it again. What's your question? Okay, so because here you see when n and m are odd, we have n equals to 2k minus 1. So this k and s has to be natural number because this is by definition. And then when k and s are natural numbers, they have to be greater than or equal to 1. Both. So k plus s minus 1 is greater than or equal to 1 plus 1 minus 1, which is 1. So this tells you this part, k plus s minus 1 is really a natural number. Hence, n plus m is even. Okay, so this is the, I think we should stop here. We've already running out of time. And please read your notes carefully because this some of the proofs are pretty abstract. So it takes time for you to really understand and absorb. So check back late tonight or tomorrow for homework.
Would it be possible to get like a group like email so we can exchange numbers to like work on homework together?
I think you can just so you don't have private communications, so you don't know each other.
No.
All right. Okay, so if you agree to disclose your emails, I can just send in homework with all your emails just listed that you can contact each other. But as I said, you can discuss your homeworks, but please write down solutions by yourself. Okay.
Okay.
Because
yeah, that'd be awesome.
I don't really want to see the homeworks are uniform. Okay. So that's that would be very bad. All right.
Okay, thanks. Yeah, that's exactly what I want. So that's perfect.
Okay. Okay, so have a good day.
All right, thank you.
Bye.
Bye.
Thank you.